Pleasure to be here and talk about a favorite subject of mine, which is the history of water on the planet Mars. This has been a controversial history because although we know Earth, pictured on the left, was well endowed with water from its earliest history, there's been a long controversy over water on Mars. So pictured on the right is an artist's depiction of early Mars. When we think from geological evidence, much of which has been accumulated in the last decade, that early Mars was very rich in water, like the early Earth. And I will talk about some of that evidence, some of which the science community has general agreement about, and other parts about which there is far less agreement. And I want to talk about this in the context of early life. Of course, we have not discovered any other life other than the life that we know associated with our own planet. But we have discovered aspects of the habitability of other worlds, and particularly Mars. So we know that life would be possible in these places, and that's the first step in our understanding. Well, this long history of understanding water on Mars began with telescopes. And looking at Mars from Earth with a telescope is a very difficult proposition because we have to see Mars through two atmospheres, the Earth's atmosphere and Mars's atmosphere. It was not until spacecraft reached Mars in the early 1960s. First one was Mariner 9. This is an artist's depiction of the interpretation, geological interpretation, made from Mariner 9. Mariner 9 took about a dozen Vidicon pictures. And in retrospect, it could not have taken pictures of a least interesting part of Mars. It only saw the cratered terrains, and it was clear that the craters had some degradation. But it was thought that that had been achieved by wind. And in the early 60s, when we had instruments that could provide some information on the atmospheric, the surface composition, temperature on the surface, it was very clear that Mars was very different from the Earth. An atmospheric pressure at the surface of less than 1/100th of the Earth's atmospheric pressure, very cold temperatures such that carbon dioxide would freeze out on the northern poles. The surfaces of the northern ice caps were covered with carbon dioxide. We only learned recently that they are actually mostly water ice, and the carbon dioxide is a relatively small percentage. But in the mid-60s, it was thought that this atmosphere, which was predominantly carbon dioxide with only traces and small amounts of other gases, was indicating a planet that was not well endowed with water. It was not until later spacecraft were able to look at the planet in higher resolution. And of course, in recent years, we have had landers like the Mars exploration rovers, Spirit and Opportunity, and very sophisticated spacecraft like the Mars Express, the current, which is operating currently in the Mars Reconnaissance Orbiter. These have transformed our view of Mars. And one of the early transformative levels of understanding came from the recognition that the topography of Mars was scoured by huge channels. The largest of these are the outflow channels. This is one called Kasai-Vallis. You see it in the Mola topography, where the high topography is in red and the low topography is in blue. These large outflow channels emanate from sources of either ponded water in large basins or more commonly from underground sources. Kasai-Vallis is about 3,000 kilometers long. This is a oblique view of the point at which this Kasai Valles is entering the northern plains of Mars, this large lowland. It has features that we argued about in the late 60s and early 70s when these were, well, actually the early 70s is when they were discovered. But it's now very clear that these were created by extremely large flows of water. Even more significant in regard to water flow was the discovery that the old heavily cratered terrains on Mars are dissected by small valleys. So here is clearly an ancient terrain equivalent to the highlands terrain of the moon, having formed about 3.94 billion years ago, but it's dissected by small valleys. And even back in the 15th century, when Leonardo da Vinci was considering the nature of landscapes, it was clear that if we have such a network, and here Leonardo has drawn two networks, one is the blood vessels of the lung, another one is the branching pattern of trees, that the breakdown into small tributaries is associated with fluid flow processes. In this case, blood, in this case, sap in a tree, and in the case of these channels, it is water that is converging because of precipitation on the landscape and converges into sequentially larger channels. So this was indicating that something was very different in the early history of Mars. This current, dry, extremely cold state could not have been the case when these valley networks formed on Mars. In more recent years, we've discovered even more remarkable things. This is a highly sinuous meandering channel. And this channel is standing in relief, and you can see there is a kind of topography which we recognize very well as scroll topography, which is created when a river meander is migrating, as shown here in the diagram. Here is Leonardo da Vinci's recognition of the migration of meander bends. He recognized this many centuries ago. And this is a property of rivers that are transporting sand and clay. The clay minerals on Mars are incontrovertible evidence of alteration of the surface materials in the presence of water. We were not able to discover these clay minerals except within the last decade, because for a long time we did not have the right instruments to detect them. It was really the Mars Express and the Omega instrument on Mars Express that made it very clear that Mars has extensive clay minerals. Another extremely important aspect of Mars, which has only become apparent in the last decade, is that Mars has extensive sedimentary rocks. Now, prior to this, it was clear that Mars had igneous rocks, and like other terrestrial planetary bodies, the surface was dominated by basaltic composition igneous rocks. But unlike other terrestrial planets that we know, we have direct evidence of sedimentary rocks on Mars. Now, this should have been obvious from the fluvial channels, but it was actually quite a while before we recognized this. This is the famous Burns Cliff. This is Victoria Crater. These sediments that were visited by the Opportunity Mars Exploration rover, they're largely big aeolian crossbeds, as shown here. But they also have small interbed units that have been worked by water, and the whole section is altered diagenetically by groundwater. So the compositions have been changed because of this interaction with groundwater. Also discovered associated with these sediments are large deltas and alluvial fans, which are clearly associated with depositional evidence. This is the Ebberswald Delta. And it's becoming apparent that, like Earth, there is a kind of sedimentary cycle that has operated in the past history of Mars. And this is a very different kind of understanding of the planet Mars than prevailed even 10 years ago. This is a map that the group at University of Colorado has recently put together showing the distribution of the deltas. Here are some images of Martian deltas at the bottom. And you can see here where a channel is coming into a basin where there's a crater, and you can see the distributaries of the channel and the sediments. These are marked by a lot of craters, which shows that this is a very ancient feature. Here's another one with the distributary pattern. The colors are a depiction of the spectral data, which shows that there are clay minerals that are present in the overbank deposits that were distributed adjacent to the distributary channels of the delta. What's shown here is topography again, with the southern highlands of Mars heavily cratered, the more lightly cratered northern plains, and the deltas are forming a band around the margin between these two terrains. This is very important in regard to the history. There's a lack of the deltas here, but this is because this is a huge volcanic complex that was in place called Tharsis. And that was in place after the development of the heavy, dense cratering. So this cratering episode that is responsible for the highland terrain of Mars is very important in regard to the history. Here is a scene about 1,000 kilometers across. In the center is one of these large impact craters, which is very important. This is called Gale Crater. It's 155 kilometers across. And it is important because this was selected for the $2 billion mission that's currently operating on Mars called the Mars Science Lander. There was a big competition for what they were going to send this very expensive rover to visit. Ultimately, Gale Crater won the composition. It did so because it has a very thick sequence of these sedimentary rocks. The number 2 site for the exploration rover is very different and has a very interesting story that is different than the Gale Crater story. I'm not sure they made the right choice. We will have to see. But certainly Gale Crater will be very interesting. You can see that it lies on this tremendous boundary that characterizes Mars between the densely cratered old terrain and then this lightly cratered northern plains. Now, as I said, when the first spacecraft went to Mars, there was even a thought that Mars was like the moon. But when you look very carefully, this doesn't look like cratering on the moon at all. The difference is there are little valleys that are dissecting the terrain. These are the valleys that were created in an ancient phase of precipitation on Mars when water converged by erosion. Another thing, more subtle, is that the lunar craters have raised rims that was created by the impact process and the formation of a transient crater as this blasts out. On Mars, many of the largest craters, the rims have been eroded down. And we think that that was caused by a phase of a lot of water erosion in the early part of Martian history. This contrast with the northern plains is very important. Remember, the deltas are located all along the boundary. And if we look at Mars from the North Pole, looking downward, we can see that this big basin that is in the northern plains has basically boundaries that separate different terrain types. Many of the depositional areas where the sedimentary rocks are located is in this boundary area on the margins of the heavily cratered terrain. Many years ago, starting in the 1980s, late 1980s, a number of people, including the research group I was associated with, the geology was seeming to point to the fact that there had been ponded water on the northern plains. And this was on a large scale, so this was given the name in a paper that I was an author on, called Oceanus Borealis. It was a temporary body of water covering about 1/3 of the planet. Now, this did not last, obviously, and it was associated only with a very early history when you had rainfall on the planet modifying these craters. That idea was very controversial in the 1980s, but increasingly the evidence has been accumulating that this seems to have been the case. One of the forms of evidence that's consistent with this is we now have very high resolution measurements of these networks of valleys. And this is a map of the density of dissection. Basically, the length of channels associated with a specific aerial measurement on the surface. So the red colors have a higher density of network. And you notice they form a band. They don't extend down into the southern latitudes. And this band goes around the margins of that northern plains. It's actually just up from where many of the sedimentary rocks have accumulated. It's also disturbed by this huge volcanic complex called Tharsis, but it seems to mark the margins of what would have been that ancient ocean. The other thing that has come about in the last decade or so is the discovery of many minerals that are associated with the interaction with water. If you read literature from prior to about 10 years ago, you will find a great sort of deal of argument that no carbonates had been discovered on Mars, and therefore Mars could not have had water, because if it rains on a surface with silicate rocks and you get weathering, you will mobilize bicarbonate and you should precipitate calcium carbonate, and this was not discovered. But that was the result of having the wrong instruments to study Mars. When we finally started to get the right instruments and had some understanding of the processes that would lead to the exposure of carbonate rocks, they had been discovered. So Mars has carbonate rocks, in contrast to much of the older literature. It also has sulfates and chlorides, and then very important is the recognition of phyllosilicates, essentially clay minerals. And you notice that they also form a broad band that is associated with this equatorial part of Mars that would be on the boundary of this northern plains hypothesized ocean. More locally, with higher resolution images, it has been possible to find that these clay minerals and carbonate zones are in layered sequences. So this is within a crater that seemed to have had ponded water within it at one time, and the mineralization is associated with precipitation from that ponded water. So the Mars Science Laboratory mission basically has produced the most sophisticated rover instrument that has been sent to the planet. The site is this 155-kilometer crater called Gale. The landing was in place in this area here, selected for engineering purposes because NASA was very worried about the potential of a failure. This would be very bad politically. And so they had a very intensive, safety-oriented protocol for landing this mission. Now, when the goal of the mission is ultimately to climb up on this large, multi-kilometer thick mass of sediments. The lower part of that sedimentary sequence, this is an image from the camera on the lander, is a layered sequence rich in iron magnesium clays with local zones of hematite, iron oxide. The upper part of the sequence, with a big unconformity through it, is layered layers that are rich in sulfate minerals without the clays. So there is a big transition in the mineralogy and presumably the climatic controls on the sedimentation that could be visited by the spacecraft as the lander as it moves up through this sequence of sedimentary rocks. Now, one of the remarkable things was the landing itself was emplaced on a sedimentary conglomerate. The mission team was actually quite conservative in releasing this information. They didn't do so until the lander was traversed a distance away from its landing site. It found some of the upturned conglomerate material, imaged it, and you have cobbles basically several centimeters across, many of them sub-rounded, that were placed with a matrix that is cementing them, although you can see that they have weathered out of this matrix. Now, the interpretation was not just based on the image from the lander, because it was recognized even before the landing occurred that the geological context of the landing site was in the distal part of an alluvial fan. So this is an image from the Mars Reconnaissance Orbiter with its cameras. And here, this spot is the landing site, the expected ellipse within which the lander would come down is shown by the black line. And this is largely a relatively low relief plain separated from the big sedimentary mound, which is down to the lower left, separated from the dangerous walls of the impact crater, where they didn't want to be near those because of the slopes. And in the distal part of the alluvial fan, you have relatively low slopes. The color here is indicating fine sediments. The alluvial fan has coarse material that have come out of this valley. There are distributary channels, which are seen in higher resolution images, but don't show up here, that must have had fines that were deposited distally. And there is a basin off in this direction where those fines accumulated, probably some of them being eroded off the clay-rich lower parts of the central mound. This zone here, these are Aeolian dunes. The lander has traversed over to this area, and it was discovered that that is probably equivalent to playa sediments, such as we see adjacent to alluvial fans in desert regions of the Earth. These playa sediments are in similar age to these alluvial fans. They're probably more than 3 billion years old, although they date to after the heavy bombardment cratering. When the lander went to that playa area, it encountered this kind of landscape, which is familiar to geologists working in desert regions of the Earth. These are sediments such as we have in playas that are rich in clays, fine material, and they have sulfate salts. Gypsum has been measured directly, and these contribute to the cracking of the ground surface. There's been secondary mineralization that produces these little rounded nodules that form in the material. This is called Yellowknife Bay, and right now the lander is, I believe, still in this area. This is some detail of the place that was not selected for the Mars Science Laboratory, called Moth Vallis. Moth Vallis is one of these areas eroded by the giant outburst floods. But what the flooding did was it exposed more ancient rocks than we have in the Gale Crater area. And there is a layered sequence in which the lower part has the iron magnesium smectites, but near the plateau surface in which this is eroded, there are high aluminum clays. This is an extremely important discovery because high aluminum clays are produced on Earth by more intensive leaching of the original silicate rocks, particularly on Earth. This forms in relatively wet environments. And moreover, they have ferruginous material in the lower part of these sections. So this is very much like a weathering profile that we would get on the Earth. And these have been discovered in other parts of Mars. So let's think a bit about the Earth, in which the history of the Earth, going back to the oldest rocks we have, is associated with the evolutionary development of a biosphere. In the case of the Earth, we've divided the history into these epochs, where we have this time scale is compressed in the early part. We have, going back to about 0.55 billion years ago, we have the Phanerozoic, in which we have complex life, multicellular life that has developed. But most of the Earth history is more simple life forms, with the period prior to this break being the Precambrian, broken into a later part after 2.5 billion years ago, where the Precambrian rocks are better preserved, and then an older period called the Archean. Now, there should be a break here because there's an earlier part even to that, to Earth history, called the Hadean, where we have no rocks. And in the early Earth, prior to about 3.85 billion, 3.9 billion years ago, there are no rocks at all. So we have no evidence of microbial fossils, nothing. We do have mineral zircon that survived the conditions that occurred starting, going prior to about 3.9 billion years ago. This was a mystery for some time, but now, as a result of studies from the Moon and from Mars, and also theoretical work, it looks as though what happened in this early time period was you had a huge pulse of impacting called the late heavy bombardment. So here's that time scale that we use for the Earth, and here's the time scale that we use for Mars. This time scale is largely developed by our recognition of different characteristics of the Martian geology. Mars also has a break about 4 billion years ago, and so it experienced this late heavy bombardment phase. So the current thinking is that when we had the accretion of the terrestrial planets, we had fantastically high impacting rates, but these dropped to a low level. We're not sure exactly what it was, but about 500 million years after the original accretion, we get a huge pulse of impacting. And in the case of the Earth, that means there's no rocks. But in the case of Mars, the intensity of the impacting was far less than Earth, because Mars is a much smaller planetary body. So its gravitational well is less. It did not attract the same kinds of large impactors. So we have rocks from Mars, if we could go there and sample them, that would come from this key time period. So this is a kind of a busy diagram that is an attempt to look at this early part of Martian history, prior to 3 billion years ago, going back to its accretion. And it summarizes a variety of forms of evidence that have been accumulating, with much of it accumulating in the last decade. Part of this evidence is this evolution of the mineralogy of Mars that has only been discovered by the spectral signatures of features on the surface, where we change from an epoch that Jean-Pierre Bigring, who was the main investigator for the Omega instrument, is called the Phylogene, the time of clay minerals. And then around this, just after this key period of the late heavy bombardment, about 3.9 billion years ago, you have a big change to a period where the mineralogy largely becomes these sulfate minerals. And these high aluminum clays seem to fit right in this time of break. That also corresponds to the age of many of the little valley networks and deltas that formed on Mars. And we think this may have been associated with the formation of the large water bodies on the northern plains. So the question becomes, what generates this? How does this get going? We think we understand the impacting flux with this late heavy bombardment peak. And we think that we know that the sparsest massive outburst of volcanic basalt occurred just after that. So now the mystery is what is going on inside of Mars to generate this. We know something about how the Earth has developed because seismology has given us an understanding of the internal dynamics of the Earth. We think we know how a planet forms, that in the early history you are accumulating formative bodies that have congealed in the early solar system called planetesimals. These will accumulate into larger bodies, and associated with the intense heating that occurs, you separate out the iron and nickel that moves into the molten core. The silicate minerals form a mantle. You develop, because of the intense heat, a magma ocean, basically a molten surface with a cooled crust that forms on the surface of that. Evidence is now suggesting that the terrestrial planets accumulated from volatile-rich planetesimals. This is also a recent revelation. Even Mercury, which was thought to be a highly refractive body, is now been discovered to have much volatile material associated with it. So this earliest history with this magma ocean may well have had above that a steam atmosphere from all of this water that was associated with this. This steam atmosphere would have facilitated weakness in the overlying cooling crust. And that weakness would, because of the convection that's taking place in the magma ocean, would result in an early form of subduction. In the case of Earth, that subduction goes to a layer about 700 kilometers deep, which separates the Earth's upper mantle from the Earth's lower mantle. But the conditions on Mars, where you have a much smaller planet, means that the subduction would go to the zone of where the core was developing. Geophysically, that's very important because you have this molten core that is forming. Above it is a mantle that is solidifying, and a huge temperature differential would develop in this cooling core. And that will induce very powerful currents in this iron-nickel core. A discovery that was made quite by accident because of a spacecraft called Mars Global Surveyor. It bent its antenna when they were trying to insert it into orbit. So they left the spacecraft in a highly elliptical orbit, meaning it could produce very high-resolution magnetic measurements of Mars. And it was discovered that Mars has a very weak magnetism that was created by the solidification of volcanic rocks through the Curie point, and the mineralization magnetized those rocks. So Mars had, in its early history, a fantastically strong magnetic field, much stronger than the Earth's magnetic field. And that's consistent with this idea that you had this core with a huge temperature differential across it. What this means is that the water-rich altered material from the surface that would subduct into the interior of Mars would put a water-rich layer around the Martian core. And you lower the melting point of this material, and so when the core gets large and the dynamo turns off because of the solidification, Mars was cooling rapidly because of its small size, you then can potentially produce huge amounts of melt, rich in volatile material that will migrate up. So it isn't a coincidence that after this magnetic field turned off, you get this immense outburst of basaltic rocks at Tharsis. And associated with that would be huge outbursts of water and other gases into the Martian atmosphere. Now, Earth has a long history of maintaining its atmospheric composition through a variety of physical processes, one of which involves the carbon dioxide. The carbon dioxide is critical to Earth maintaining its greenhouse effect that has resulted in what has been demonstrated geologically, that you can trace the presence of water on the surface of the Earth not only back to the oldest rocks, because some of the oldest rocks are sedimentary rocks on the Earth and placed in water. You can trace it back even prior to the late heavy bombardment, because the isotopes that have been found in the zircons that date prior to the late heavy bombardment show large amounts of water alteration. So the early Earth seems to have had, even when the sun was fainter in its early history, liquid water on its surface. And the way that is maintained is basically the processes that can remove carbon dioxide from the atmosphere. If you have an atmosphere with a lot of water in it, you're going to form carbonic acid that will basically mobilize bicarbonate, which will precipitate in the Earth's oceans. But because Earth has subduction going on, you metamorphose that in the subduction zones, and you release carbon dioxide into the atmosphere of the Earth through volcanism. So this is illustrated here in this diagram, simplistic, where you've got a subducting plate here. Volcanoes develop associated with the zones of subduction, which today surround the Pacific Ocean. The Earth's atmosphere on tens of millions of years maintains a concentration of carbon dioxide. Of course, it has water vapor because it has this ocean over the surface that's evaporating. This precipitates, forming a weak acid that will migrate bicarbonate into the water body. It forms calcium carbonate-rich rocks, which get subducted, and you have a cycle that's maintained. Now, in the case of Mars, Mars is basically frozen. It has, we have demonstrated now with multiple techniques, lots of water in the subsurface, but the only water, large quantity of water on the surface is at the poles in the ice caps, which are up to 2 kilometers thick and are mostly water ice. So how does Mars change? Well, Mars is a one-plate planet. The heat release process for Mars is stagnant lid convection. There's convection in the deep mantle and then conduction through the one-plate surface. This means that the heat that is developing internally in Mars is released episodically. So when that happens, you basically disturb this subsurface reservoir of ice and probably also carbon dioxide that may be within the Martian ground ice as a gas hydrate. And you can then put these gases, which are going to be greenhouse gases, into the Martian atmosphere. So temporarily, you can create, maybe on timescales of tens of thousands or a million years, an Earth-like condition. But unlike Earth, this is not stable. On Earth, this system, this Earth system has largely maintained this kind of state. On Mars, this, because of the distance from the sun, this will eventually collapse back into this cold state. Well, we have learned relatively recently that Earth itself collapses, but it does so in a different direction. Earth, in its earliest history, basically collapsed from a state like this into what some have called a snowball state. And this snowball state was recognized by climate modelers when they found that because of the distribution of continents and the ability of the hydrological system to pull carbon dioxide out of the atmosphere, you could get a runaway effect of forming ice on the continental areas, which would change the surface albedo, and you could get a runaway cooling and eventually put ice over the oceans. The climate modelers didn't realize the Earth couldn't stay this way because the volcanoes on the Earth continue to put carbon dioxide out, and the snowball state collapses back to the greenhouse state. So what about Mars? Well, first let's look at this, the evidence for this Earth snowball state. In the late Precambrian, very bizarre circumstances were found with clear evidence of glacial sedimentation. These are erratic compositions within glacial diamictites, and this was indicating very cold conditions, and the paleomag showed that this occurred at equatorial latitudes, which should have been the warmest. So the Earth's temperature, shown in the plot here, collapses to an extremely cold state. And it stays this way for maybe a million years or more. And then the climate changes because these cold glacial sediments are overlain by carbonate rocks, which form in very warm conditions. So the Earth flips from this cold state to a very warm state. A super greenhouse develops. Another aspect of this cold state is that you get a peculiar kind of sedimentation called banded iron formation, which only occurs in the Precambrian part of Earth history. Basically, the ocean goes anoxic because of the cover of ice over it. And here is one of these late Proterozoic banded iron formation, and there's an erratic boulder in it. Here's another view, South African penny coin, and this is a dropstone from probably berg ice that was over this ocean. This is banded iron formation. So there was an anoxic ocean underneath. When the climate changed back to oxygenating the ocean, this iron oxidized to hematite and limonite, so the color was then changed, but iron was mobilized under those conditions. Now, these banded iron formations, we find them mainly in the older part of the record. Most of the Earth's iron ore comes from these zones. And then we find in this snowball phase, the blue lines are glacial periods in Earth history. You notice superglaciations of the snowball phase. We have later phases, including one in relatively recent Earth history. These are closely related to stresses that affected the Earth's biosphere. So Earth has this oscillation that goes between the between greenhouse states, and it flips from a greenhouse state to a glacial state. So here's a cartoon that basically illustrates this Earth flipping process, where the stable condition for the Earth is a kind of a greenhouse maintained by this cycle involving carbon dioxide, that in the early part of Earth history was able to flip to a kind of icehouse state, and essentially Earth became Mars-like, but only for a relatively short time, because the volcanoes continued to put out carbon dioxide, Earth developed a super greenhouse that basically removed the icehouse condition and then went back to its stable state here. In the case of Mars, being further from the sun, the stable state is with the ice in the subsurface of Mars. It's stable in the icehouse phase, but the internal dynamics of Mars are promoting a disruption of this and a temporary quasi-stable state that is similar to the long-term stable Earth state. So Mars is flipping out of a super icehouse into a kind of cold Earth, a kind of glacial state, more like the Earth's ice ages. So we have this Earth-like planet, Mars, which has a history of water, which is critical for life as we know it because of the association of life with that water. And it, in its early history, had a kind of strange Earth-like behavior. Now, our understanding of this is, of course, important for our understanding of the Earth, but it's also important for something that is accelerating very rapidly, almost as we speak. And that is that we are discovering around nearby stars solar systems. And initially, of course, the first discoveries were of very strange planets called hot Jupiters, which are big gas ball planets that are associated with stars. And they were found first because they were easy to find by the techniques. But we now have much more sophisticated procedures. Particularly, the new instrument is called Kepler. And it is finding that nearly all stars of a certain size have planetary bodies around them. And the other thing it's finding is that nearly all of them are planetary systems with rocky bodies analogous to our own solar system. So this is one that has been in the news. So here's a comparison to our solar system with a certain size star and the planets we know. This is a smaller solar system because it has a much smaller stellar object, and it's got big rocky body planets that surround it. What we know about them is limited to their density, their size, but they're consistent with these things being water worlds. In other words, they are analogous to this early Earth and this early Mars that I've been talking about. And certainly NASA, and I think all countries that are interested in this, are trying to develop the capabilities of discovering these. As the late Carl Sagan would say, we've got billions and billions of them. So the potential is there to learn a tremendous amount about Earth-like planets. And that can only help us understand the Earth. And of course, Earth is the planet with life. We are evidence of that. And so as we discover these habitable zone planets, analogous to our own solar system, we're going to have a huge empirical database to understand the relationship of life to a planet. Mars is really just the first step in this. This is a tremendous adventure, and of course, you all here are at the frontier of astrobiology, which sometimes gets criticized as the science without a subject, but you've got a huge potential subject out there, because if you think of it broadly in terms of a planet and the development of life on that planet, it's basically the scientific endless frontier. So thank you very much for my chance to talk to you a little bit about some of my ideas about the planet Mars, and I'll be happy to answer any of the many questions that there should be about the things I've said.